j'accueille maintenant Daniel Lanzillotti KIMURA du C2N à Saclay, qui va nous présenter une application de photonique intégrée particulière autour du son et de la lumière.
Bonjour à tous, merci Adeline et Sylvain pour cette opportunité unique. Je vais faire ma présentation en anglais, j'espère que ça ne dérangera personne. Je sais qu'il y a quelques étudiants qui ne parlent pas couramment français, donc ça va aider. Good afternoon everyone, my name is Daniel Lanzillotti KIMURA. I'm a researcher at the Center for Nanoscience and Nanotechnology in Palaiseau. It's very weird to talk about acoustics in an optics meeting. So I will try to do the link between the two domains. My talk is about nanomechanics, nanophononics, and nanoacoustics. And before starting with the scientific part, I would like to thank my team, who are the heroes of the work I'm going to present, and some of the ex-members of the group who contributed to some of the results I'm going to present to you this afternoon. Of course, I would also like to acknowledge the funding sources. Without that money, it's impossible to do experimental science in France and anywhere around the world. The work couldn't have been done without the collaboration of many people in the C2N and an extensive network of international collaborators, so I thank them all. In particular, for this presentation, I would like to thank Aristide Lemaitre for the growth of the sample and the team of Isabelle Sagne for the etching of the nanostructures I'm going to show. So let's talk about nanophononics. What is nanophononics? It's the engineering of acoustic nanowaves, of acoustic waves at ultra small scales and ultra high frequencies. And why do we care about phonons? We care about phonons because every single property, including optical properties in its solid state, that are determined by the position of the atoms, can be modified or affected by the presence of a vibration of a phonon. In addition, if we go into the ultra high frequency domain, there are two main characteristics that have many implications. The first one is the short wavelength in the nanometer scale. That means that if we use phonons to probe things, we can localize or detect things at ultra small scales. And we can use phonons to develop integration, interactions with other excitations. And the ultra high frequencies have two implications. The first one is that we can modulate other properties at ultra high frequencies of the order of from 1 gigahertz up to 1 terahertz. And the second one is that we automatically can enter into the quantum regime, into the mechanical quantum regime, because of the lower occupation numbers. In this way, if we assume that phonons can modify other properties in the solid state, we can assume that we can make interactions with the magnetism, the nanoelectronic engineering, with optics. We will find applications in quantum technologies. We can use phonons to simulate other solid-state excitations or dynamics. And finally, of course, phonons are determinant for the thermal management properties of a material of a nanostructure. When we talk about nanophononics, we talk about a very particular frequency range in which standard techniques are not usually available to detect or generate excitations. In principle, one can think of optoacoustics or photoacoustics, optomechanics, but what happens there is that the frequencies are mainly limited by the smallest pitch that we can make in a structure. On the other side, we can think about the detection of vibrations using standard spectroscopic techniques like Brillouin scattering or Raman scattering, but in that case, the frequencies are too small or the devices are too complex to integrate them with the standard measuring techniques. We cannot use techniques from acoustics. We don't have efficient transducers to generate sound and detect sound like speakers or buffers or things like that. So we are forced to rely on techniques based on optics. So we need to use optics to generate, control, and detect acoustic vibrations at the gigahertz scale, in the gigahertz range. When I talk about nanophononics, in particular in my team, we work with wavelengths of the order of 1 to 100 nanometers, acoustic wavelengths of this order, and frequencies from 1 gigahertz up to 1 terahertz, more or less. Another important detail of what I'm going to talk about is that we use acoustic phonons and not optical phonons. This is a question that I usually get in all the conferences, and the reason is that we can engineer the dispersion relation of the acoustic phonons, while the optical phonons cannot be modified in a very reasonable or useful way. So let's move forward with open challenges in nanophonics. And this is a very subjective view. This is almost an opinion from my team. I think that there are three main challenges in nanophonics, and the first one is to develop acoustic phonon transducers. As I mentioned before, standard transducers cannot be used to generate or detect phonons. The second one is the control of the phonon dynamics, is to teach the phonons how to do things that we want them to do in solid state that they don't usually do. And the third thing, which is my dream, my current projects, is to develop tunable, programmable, and active circuits that use phonons as carriers of information between different nodes in a network. And for all this, we need light. That's why we are in this conference. So the outline of the talk mainly deals with two main parts. The first one is about fundamentals on how to control acoustic phonons in nanostructures, in planar nanostructures. The second one is to move into the 3D world and how to integrate these devices into realistic systems that use phonons for something else, or that could use in the future phonons to do something else with other excitations. And finally, I will move into the short conclusions and perspectives. So let's move on with the first part of the engineering. Fundamentals. This is solid state 101. We have a dispersion relation of a bulk material. For acoustic phonons, it's a straight line. It's a line that means that for most of the frequency ranges that we are interested in, the speed of sound is a constant. If we introduce a new modulation into the system, for example, by structuring the system in the shape of a superlattice of two different materials, we will fold the dispersion relation, we will generate a new Brillouin zone, and we will open gaps at the edge and center of the Brillouin zone. This is exactly the same that happens with photons and with electrons when we have a periodic system. If we look into the details of what happens at the edges and center of this Brillouin zone, we observe these gaps. These are regions that have associated no-wave vectors that can transfer energy into the system or through the system. In reality, we don't have infinite superlattices. We have finite-size superlattices, and the band structure is just a model that we use to understand the behavior of these systems. In reality, what we have is reflectivities and transmissions through the structure, and the high reflectivity regions are zones, frequency ranges, that are associated to these band gaps for acoustic phonons. What is interesting about this is that phonons cannot propagate, but they are not absorbed. This is an almost perfect reflection device. So we will call them distributed Bragg reflectors, in our case, acoustic distributed Bragg reflectors, that are the fundamental and simplest device that you can use for phonons, to reflect phonons, to change the wave vector of the propagation of an acoustic wave at ultra-high frequencies and at the nanometric scales. So, of course, we can do an engineering of this system and change a bunch of properties. We can change the materials that we use, the number of periods, the higher the number, the higher the reflectivity. And the relevant parameters of the materials that we use are the mass density and the speed of sound of the materials that we use. In particular, what we actually care about is a contrast in these properties in the materials that we are using. The second question is, how do we generate and detect these acoustic phonons? And as I mentioned before, we can use Brillouin scattering or Raman scattering, but we can also use a time domain, time resolve technique, the pump and probe. The idea is very simple. We have, maybe I can use. The idea is very simple. We use a pulse laser, and we send the first pulse that will generate acoustic phonons into the sample. These acoustic phonons will modulate the optical reflectivity of the system, and a second pulse will be used to probe the instantaneous optical reflectivity of the structure that we are studying. In this way, if we change the delay, I came back to my original position. If we change the delay between pump and probe and we repeat the experiment, we can reconstruct the optical reflectivity affected by the presence of the coherent phonons. We perform a Fourier transform and we recover the frequencies of the phonons that were modulating the optical reflectivity of the system. In this particular case, we have a system that was used to reflect or interact with phonons of around 1 terahertz. The second device that we can think of is a resonator, a Fabry-Perot resonator. We know how to create mirrors with distributed Bragg reflectors. We can phase 2 mirrors separated by an acoustic spacer, and we generate the equivalent of a Fabry-Perot resonator for terahertz acoustic waves. In this system, we generate an acoustic mode in the high reflectivity region of the mirrors, and if we plot the strain distribution in the system for the particular confined mode, we observe that the strain is localized at the center of the acoustic cavity. We can perform a pump and probe experiment over the system, and you can see in the lower right part that there is a spectrum characterized for a family of peaks, but the principal peak is associated to the confined acoustic phonons in the acoustic nanocavity that we designed. And this is using a single pulse for pump. We use a pump pulse that will generate phonons, we observe how they evolve, and then we start again the experiment. But we can do something more interesting, which is use 2 pumps that will make the phonons interact. And in this sense, what we will use is 2 delayed pumps. The first one will generate a population of coherent phonons. We will wait a little bit, and we will send the second pulse. The second pulse will generate the second population of acoustic phonons that are also coherent and that have a relative phase with respect to the first one. That means that changing the distance in time between the 2 pulses, we can make them interfere either constructively or destructively. And these are the 2 examples that I show you here. In this sense, we have a new tool that allowed us to amplify, enhance the population of phonons that we have confined in the cavity, or kill them all, or do something intermediate. We can synthesize a pulse of phonons, of coherent phonons, inside an acoustic cavity. This is not the only kind of acoustic cavity that we can have. Over the last 15, almost 20 years now, we realized that gallium arsenide and aluminum arsenide, the star materials for optoelectronics, are magic materials for optomechanical properties. In what sense? In the sense that the contrast in the optical properties is exactly the same as the contrast in the acoustic properties. And meaning that if we optimize an optical cavity to confine photons in the near infrared range, we automatically get an acoustic cavity that will confine phonons in the 18-20 gigahertz range. And the magic coincidence doesn't end up there. The idea is that if you plot the confined acoustic mode and electromagnetic mode, they show a perfect overlap in space. That means that we confine frequencies, but we confine spatially the 2 excitations in the same region of space. So we have a magic structure that allowed us to automatically get a perfect optomechanical system in the sense of overlap between light and sound. We tested the functionality of this device by taking an almost 30 years old sample, which was originally an optical cavity. We characterized it optically and then acoustically, and we observed that we were able not only to measure the fundamental confined acoustic mode at 20 gigahertz, but also the 3rd harmonic and the 5th harmonic at 60 and 100 gigahertz. So this means that by using one of the most well-known materials for optoelectronics, we can do ideal optomechanical systems in which the interaction between light and sound is automatically enhanced. So this is the very fundamental of nanophononics. We can do a bunch of things. I show you how to create phonon mirrors based on superlattices. You can do acoustic cavities based on the Fabry-Perot resonator concept. And then you can think of, use your imagination about combining single elements into more complex structures and do Bloch resonators, topological structures, or even combining optical cavities with acoustic cavities. I will not go into the details. I will just move forward into the most interesting part of the talk, which is moving into the 3D world. Everything that I said about the perfect overlap between light and sound is valid for one dimension, for infinite superlattices in space or wafer-size samples in which we probe with a laser which is a few microns. So the system is infinite in the in-plane direction. Let's now see what happens when we go into three-dimensional structure and when we confine acoustic and optical waves in 3D. So the first step to go 3D is to etch the sample. So we take the standard multi-layer, we do an optical lithography or an electron microscope lithography, electronic lithography, and we etch the material in the vertical direction. What we get here is, in the optical domain, a contrast between in the lateral direction, a contrast in the indices of refraction of the light and air, so we get the equivalent of an optical fiber. And in the vertical direction, we have the Fabry-Perot resonator structure. For sound, the things are slightly different. There is no penetration of phonons in the air. There is a perfect reflection, so the boundary condition is slightly different. But in the vertical direction, the Fabry-Perot resonator works the same. If we plot the strain profile and the electromagnetic intensity inside the structure for the confined mode, we observe in the phononic and the optical cases that there is an almost perfect overlap. If you are back in the auditorium, probably you will see that it is exactly the same. It is not. It is very good overlap, but there is a modulation in the acoustic case that doesn't appear in optics. And that's related to the Poisson ratio of the material and the difference in the boundary conditions. So we tried this this three-dimensional structure, and we observed that we were able to confine acoustic phonons and confine near-infrared photons in the same three-dimensional system. So we were able to control the local density of states of acoustic phonons and near-infrared photons with a single and unique structure. So why do we care about micropillars? Basically, there are a bunch of applications that you will see over the week in this conference. They can be used for single photon sources. The previous speaker mentioned Quandela. Quandela is developing single photon sources based on micropillar structures, very similar to the ones that I was showing here. There are polaritonic systems, optoelectronic devices like lasers, VCSELs. They are used for simulation platforms and other quantum technologies. So acoustic micropillars, optical micropillars are extensively used, but not extensively used as acoustic resonators, as I showed you before. The open question is how to perform a quantitative transaction and how to integrate them into other optical systems. And for that, we got a very stupid problem at the beginning of the characterization, and is how to couple a laser into a small micropillar and get an acoustic signal which is of the order of 10 to minus 7 of the scattered standard optical signals. And the problem was a problem of stability, of alignment, and repeatability. The solution was very simple, was to come with a single mode optical fiber, measure the optical reflectivity of the system, and when we get a dip, it means that we are coupled to the optical mode. So we glue the optical fiber into the micropillar, we cook it, and then the system is fixed forever and ever. That means that there is no further alignment, and I can use my acoustic phonon source to do some characterization experiments, or I can send it to Bariloche or Australia, and they will repeat exactly the same measurement with the same intensity and spectrum shape. So we were able to reproduce the measurements with very much higher quality, as you can observe in this experimental spectrum, which looks like a theoretical curve, but it is not. And what is absolutely magnificent is that we usually have an stability in the lab of the order of a couple of hours, and then we have to realign or readjust something. And with this integrated source of phonons, we were able to perform experiments over 48 hours without touching anything. Actually, if you look at the intensities measured in the top panel, what we observe is that there is a little fluctuation, and the fluctuation is periodic, and it corresponds to the variation of the room temperature affecting the laser intensity, and not the alignment of the hour source. So that's one way of going 3D. The other way is to, instead of confining in all the dimensions, to confine in only one dimension and generate an acoustic waveguide for acoustic phonons working at tens of gigahertz. And for that, we just simply lithography a waveguide over the same structure. In the vertical direction, the Fabry-Perot will confine the phonons. In the horizontal direction, the phonons will propagate pretty much in a similar way as photons. So here I show you one example. I will go fast to reach the last point. Two examples in which we perform local pump and probe, and we observe that we generate phonons and the signal decays in an exponential way. That means that the phonons are escaping the spot in the lateral direction and towards the substrate. If we perform a different experiment in which we pump phonons in one point and we probe the presence of the phonons in another point, we get a signal that looks like a time-of-flight experiment. The phonons arrive, or the signal of the phonons arrive later in time. Don't get too excited. This is not a time-of-flight experiment. This is a much more complex thing that took us over 2 years to understand. So the first step is to perform COMSOL simulation to see what's happening here. We generate the phonons. This is a strain. We observe that there is a vertical dynamics that we don't really care about, and then a lateral dynamics in which the system starts radiating phonons into the waveguide. If we take into account the repetition rate of the laser and the spot size and several other minor details, experimental details, we were able to simulate almost perfectly the dynamics of the system. But what we get here is not a time of flight, but an interference process between multiple pulses of the laser coming one after the other. Actually, when we go more into the details with a cleaner sample, we observe that the signal is spread over the 12 nanoseconds, which is the period of the repetition rate of the laser. That means that there are phonons all of the time, meaning that we excite the source of phonons more rapidly than the decaying time of the source. So what we are doing is synthesizing a source of phonons, a continuous wave source of phonons, into the waveguide. And we are able to measure the decay rate over the length of the waveguide. So we have a resonant excitation, we have a continuous source of coherent phonons, and we have a remote measurement, meaning that at room temperature, we are able to measure phonons of over 20 gigahertz in a relatively easy way. The next experiment, and I will finish with this, is what I consider one of the most beautiful experiments in physics, not ours, in general, the interference effect, the spatial interference effect. And in this case, what we will do is to simulate or to actually perform the experiment of two coherent sources separated in space interfering. To do this, we will use, instead of one pulse of excitation source, two pulses of pump, separated 18 microns, and we will measure exactly what happens in between them with a probe. And what we observe here is that at the center of two coherent sources, exactly at the center, if they are in phase, we will always get a maximum of the signal, a maximum amplitude of the oscillation. Then we can delay one of the sources, set the phase of the second source by setting the delay between the two pumps. So there is a small delay between the two pumps. So the sources will have relative phases. And we can reach a condition of destructive interference between the two sources in the point at the central of the structure. So we have two conditions under which we can enhance the presence of the phonons or annihilate the phonons in a remote way. So we have a remote control to control acoustic phonons in a nanostructure system. Of course, if this is an interference, we should observe some kind of sinusoidal modulation with the spatial or time distance between the two sources, and it is exactly what we observe. In the left part, you can see the experimental data showing the single source case, and the two sources interacting, in which we observe the interference oscillations, that's right. And in the right-hand side, the COMSOL simulations, in which we simulate exactly the same experimental conditions. The contrast is not the same, simply because the light is interacting in different ways at different points. The coupling into the optical waveguide is slightly different, but overall the behavior is perfectly reproduced by the experiments. So let me move into the conclusions. Very rapidly, I show you how to generate, detect, and manipulate acoustic phonons in nanostructures, how to confine and transfer ultra-high frequency vibrations in a vertical structure or in a three-dimensional structures between two different points. I show you very briefly, how to engineer optophononic interactions, and believe me, there are some results that show that phonons can be used as a new simulation tool. With this, I want to thank you for your attention, and I keep open for questions.
So thank you very much, and we are given some time for one question before we break for the feed. Okay, so maybe I can give it a go. So we talked a lot before about nonlinearity, right? And here everything you show is linear. So can you maybe hint about how to include nonlinearities and how to bridge some of these effects to?
So the nonlinearities with phonons come basically from anharmonicities of the lattice. And either you need huge anharmonicities or very long distances. The easy way is to go into really long distances by, for example, transmitting phonons through a substrate. 300 microns for phonons is a lot. Usually they die in the process or decay. But if you have a clean substrate, like an MBE substrate, and you perform a transmission experiment, you can measure the generated spectrum and the arrival spectrum, and they are completely different due to nonlinearities. Controlling the nonlinearities is a different story. It's much more complex than with light, or we are not mature enough as to control the nonlinearities with acoustics.
So, okay, so let's close the session, and thanks both speakers again. Thank you very much. Merci à tous, et la session reprendra dans une demi-heure avec l'astromécanique et la